make a start. Cool. So there's not going to really be a lecture portion to this part of the or this week's class anyway, unless we need to deviate on and rebuild some fundamentals. For this lesson and the next class too are going to be essentially review chapters. So one is literally going to be the chapter 8 review, and the other would just be like a full review class, and we can focus on any particular topic you guys want, or we could just keep working on these, because if we take a quick scroll through, there are a lot of questions in the chapter 8 review, even including some algorithms and pseudocode related stuff as well. I don't think we need to put too much into that specifically, but if we do need to revisit that, that's totally fine as well.
Chris.
Yeah.
I don't know if this is possible, but I'm noticing that it's just me here today. I was wondering if I'd be able to go over some things that I think I'd need some help with you today, like after the reviews and everything.
Well, yeah, I mean, I was going to go through like
Yeah.
question forever, basically.
Yeah.
So if you've got something you
Oh,
want to look
okay.
at specifically, then yeah, we can do that.
Oh, okay. I think that works because this will cover everything from 1 to 7, right?
Yeah, correct.
Oh, okay. Good.
Is that something because I noticed I keep forgetting to check the Google form thing. Is this something you've submitted, or do you just have something in mind you wanted to have a look at?
No, I was just thinking of I was just struggling a bit with logs and circ functions.
Logs and circ.
But
Okay.
yeah, but I think you'll cover that anyways. So.
Yeah, okay, so I can basically pick out all the ones that have logs and circ revolved around, and then I suppose we'll backtrack into some lecture portion stuff if at all relevant. Cool, okay, so maximal domain, nothing necessarily going on there. Okay, so the first thing, when you're saying logs, are you including exponentials in that?
Yeah, sure.
Sure, okay, cool. So let's see what this first exponentials related question. By the way, Anya, we're just sort of doing an overall chapter review of all chapters 1 through 7, essentially. So there's a lot of content, but we're just sort of narrowing on particular parts, namely the exponentials logarithms, as well as some of the circular function stuff we were doing a bit earlier. Okay, first things first. So while there is an exponential in question 4, a lot of this is actually around the inverses of that function. So I guess first things first, just broadly speaking, what do we typically do when it comes to finding the inverse of a function? This notation, f inverse of x, always tells us to do
swapping the x and y.
swapping the x and y, precisely. So in this case, we have f of x, but we can just treat that as if it says y. And the first step for finding any inverse, as you said, just swap the x and y around. So let's do exactly that. That'll mean we have x equals 2e, yeah, okay, 2e to the 3y, let's say minus 1. That's the first step of solving or creating the inverse function. What's the next and final thing we have to aim for when it comes to inverses?
Solve for y.
Solve for y is correct. Yeah, so 2 stages. Anytime it says find f inverse, f to the power of -1, first things first, swap the location of the x and y in the function, and step 2 is to now get that y back on its own. As for how we do that with exponentials, this is where the relationship between exponentials and logarithms is going to come into play. So what you'll find is that when you're doing the inverse, you'll go from exponential to logarithm or from logarithm to exponential. And we'll see what that looks like shortly. First, we're going to do some rearranging. So you want to get the exponential term on its own, which means we're going to now have x plus 1 divided by 2, moving this minus 1 and dividing this 2, equals e to the 3y. Now the conversion. There is a way to convert from exponential to logarithm form. Does anyone remember what that's going to look like?
Would it be log 3x is 3y?
Log 3x equals 3y, like that.
Yeah.
It's a
Oh
little
wait,
bit
I think
off.
I'm.
So you need to make sure everything you've got written here is rearranged in some way. So kind of missing a fair bit over here, and there's also no e involved still. Do you want to give it another shot, or maybe someone else? More or less, the idea is we're going to have all of these terms still involved somewhere in there, and there's a bit missing.
Um.
On the screen share, I'll also have the conversion formula for you guys to have a look at. Got the formula as well as an example to look at.
Is it 3y is log e of x?
That's a lot closer. So instead of putting a log 3 there, we're going to have a log e, or natural log, depending on how you want to write it. There is still this that needs changing. So
Oh, is it y equals 1/3 log e of x?
so this
Or is that
will go
still
over. Yeah, this will eventually go over to be a third. You're right. It's this thing here in the bracket that needs to be this whole thing here. So if we think about what's on the screen share, the y equals log ax, basically whatever's on that left hand side or opposite the exponential, that goes in the bracket. So it's not just the basic variable that goes in there. Whoops. No, it's not just the basic variable that goes in there, it's the entire left hand side. And so what that would end up looking like for this circumstance here means you're still going to have the 3y split off on its own like you did. You're still going to have the natural log, or log e, however you want to write it, but you're going to have the x plus 1 over 2, the entire thing in the bracket instead. And then, yeah, to wrap it up, just like you mentioned before, you'd want to bring that third over. So you now have, whoops, not with an equal sign there, you'd want to have a third natural log x plus 1 over 2 is equal to y. Although at this stage here, you'd now want to rewrite that as f inverse specifically because it asks you to find f inverse. So you'd have f inverse of x is equal to a third natural log x plus 1 over 2. So that's all it is, really. Looking at that conversion formula, knowing how that works, you're essentially just swapping all of the terms in your exponential equation into a slightly different spot. The first bit goes in the bracket, the thing in the power goes on its own, and whatever this is goes in as the base of the log, which that's a shorthand. Natural log is the same as log e. Any clarifications there so far? If not, feel free to... Oh, there's still the domain part of it. So moving on to the second part of it, a lot of the time when you're doing questions around finding the inverse, sometimes they will ask for just the rule, in which case we would be done here. This is the rule of f inverse. Sometimes they ask just find f inverse, and they won't say anything else. Under those circumstances, you have to also give the domain as well. That is an important part of the function. What do we know about finding domains or even ranges of inverse functions? There's a specific rule around it. Which I also have highlighted up on the screen share if you would like to copy off of that.
The domain and range will switch places.
That's right, domain and range will switch places. So basically, the domain and range of the original function become the range and domain of the inverse function. They swap. So, for instance, if we know the domain of our original function f of x is all real numbers, as we can see from this statement here on the screen share, that means the range of the inverse is therefore going to also be all real numbers. It's going to be a direct copy. What's a bit more challenging is we have to find domain of f inverse, which means we need to find range of f. Range of f being all the possible y values that it can have. What is the range of f, or how could we potentially find it? Range being all the possible y values of the graph.
Could you repeat the question?
Yes, so we're trying to essentially find our domain of f inverse, and what we just discussed was it's the opposite of the original. So in order to find that domain of f inverse, we're now looking to see what's the range of the original, what's the range of f of x. Because if we can find that, then that is therefore going to be the same as the domain of f inverse. So the question now is, how or what is the range of f of x? Or at least, how could we potentially start finding it?
So f of x is an exponential function, so it will have it will approach 0, but since it has a vertical translation of -1, it's going to approach -1. So excluding -1, the range is -1 to infinity.
That's exactly right. Yeah. So just knowing roughly what the shape of the exponential is and looking at the transformation factors that are involved, that will allow you to get a picture in your mind of what the range is. I've drawn a rough idea of what the exponential is. It may or may not curve exactly like this, but it's all we really need. That shift down by 1, the -1, implies there's that asymptote that you were mentioning. And because it's base e, and not a base between 0 and 1, it's going to do this sort of thing where it shoots up and to the right in a concave up way. That'll shoot on forever, and as we said, it'll asymptote at -1. So therefore, if we know the range is now from -1 to infinity, that means the domain of f inverse is the same thing, -1 to infinity. You can use this notation, that's fine. Usually we do stuff like x is an element of, but when it comes to specifying like your inverse function related stuff, it tends to be better to say, hey, I'm specifically talking about f inverse, so that's what I'm looking at. You could even do the x is an element of after the colon as well if you wanted to, but a lot of places aren't going to be marking you that harshly on things. But yeah, okay. Sketching the graphs, so yeah, why not? We've kind of already done one of them. So we've sketched the graph of f of x already, just briefly. We also have the graph of f inverse to sketch, at least as far as 4b is asking us to do. How do we go ahead and sketch logarithms? What kinds of things do we need to start looking at?
Vertical asymptote.
Yeah, vertical asymptote. How do we find that?
We look at the translation.
Yep.
Horizontal translation.
That's correct. What do we have as a horizontal translation? It's a cheeky one right here. there's a piece of advice I usually give in a lot of the sketching stuff. We did this yesterday as well, which is removing coefficients. What's our actual horizontal translation here?
-1.
Yes, we're shifting left by 1. So even though there's this divide by 2 here, that's technically already really factored out. Right, like another way of rewriting that would be having half out the front of x plus 1. So it's already actually factored out there. Written that way, it can be a bit confusing, but when you rewrite it, you can now see very clearly, yep, x plus 1 means a shift left by 1, which means we should now have our vertical asymptote at -1.
The vertical and horizontal translations will also switch places, right?
Yeah. So one of the reasons why they're getting you to graph this on the same set of axes is to show you the inverse by nature is a reflection across the line y equals x. Another way to think about that is you're just swapping every single x with its corresponding y value, which is why, like you identified, this horizontal asymptote of -1 is now becoming the vertical asymptote of the inverse. And so what we should end up having, if we've done things correctly, is we have sort of like this mirror of y equals x, and what we end up drawing should be roughly mirrored in that way. So it'll asymptote out like that and that. And basically, like if I were to realign this, so this is now the center, everything should be reflected perfectly along that line. So that's what they're trying to highlight there by getting you to do it on both. Another way that helps, not just with asymptotes, but also with key features. We kind of didn't bother doing the x and y intercepts just yet, but if we had them, whatever this intercept is, the y-intercept of this, becomes the x-intercept of that. Whatever the x-intercept of that is, becomes the y-intercept of that. We're flipping every single x with its corresponding y value, and so on and so forth. We could do x and y intercepts if you like. It is the same for every function ever. We're just substituting x equals 0 and y equals 0. So let me know if you want to actually do the arithmetic on that. Otherwise, I think the last one we'll have a look at from question 4 will be part C. And less about sketching it, more about talking about it, I think. Have a think about, I'll say, this can be solved without knowing anything about what f or f inverse are. There's some math theory behind what this is going to look like, and it's independent of what you actually have for f.
Is it x?
It is x.
Y equals x?
Yeah. Do you remember why that is?
All the things cancel out.
Yeah, they're basically all going to end up cancelling into each other. I think I have this in my composite functions section, maybe? Not there. Okay, maybe it's in here somewhere. No, I don't. Okay, so I'll write it out. Basically, what he's talking about there is the property that y is equal to f of f inverse. That always comes out to be x. Now, more specifically, if this was anything other than x, that would also be reflected over here. So let's say in there was like 5x minus 3, this bit would also be 5x minus 3. This is two things stacked onto each other. So we've already talked about f and f inverse being symmetrical about the line y equals x. What we're looking at here is composite functions, which is shoving one function into another function. So if you think about what's happening here, in here you're swapping the x and y, and then subbing that into the original function again. By whatever arithmetic is going on there, you're essentially reversing it and then cancelling out what you've essentially done back to just whatever the original variable is. Now, it's a neat little trick. It works in both that way and if you have f inverse on the outside as well. So if they're in the opposite direction, this also works as well. It's a neat little trick you can use for those kinds of things. What is going to be different between them is what the domains of each are. Does anyone remember the rules around composite function domains? Because they are going to be different to each other, even if the rules are the same. We might have looked at this like at the very beginning of the year, so let's see how good memory is. Okay, so it's worth having a think about what a composite function actually is. And I kind of briefly talked about it just there, where you're essentially putting one function into the other. A way I like to describe how composite functions work is you essentially start with some, even if we just sort of take another step back and just think about functions in general, you have some x value, you feed it into whatever function you have, and it does some magic in here, and out comes a y value. That's a really basic way of thinking about a function. All right, something as simple as 2x, you feed some x value in, it gets multiplied by 2, and then out comes that multiplied value. This is just a broad statement for any possible f of x. What a composite function is another stage in between there. So you have an x, it gets fed into whatever the inner function is. So let's say we're looking at this one. It gets fed into the inner bit, which is f of x. Whatever comes out of that then gets fed into the outer bit, which in this case is f inverse of x. And then only then do you finally get your y value. This is different to if we had them in the other order, because this order flips. F inverse goes there, f of x goes there. Same x, same y. The reason why it's different, this function can only accept a certain domain. This function is probably going to expect a slightly different domain. So what can actually fit in at the very beginning of that procedure is dictated by whatever the first function is in the process. So we had f of x, the original f is the exponential, where is it? There it is. It had a domain of all real numbers. So if we had this procedure, anything can fit in there. However, if we had the opposite, f inverse of x, that had a domain of -1 to infinity. This one can only have -1 to infinity fitting into it. So for that reason, even though the rules end up being the same, you sketch them over different domains because of this initial bottleneck, basically. So just for clarity, this sequence, the first sequence here, is related to this one because f is on the inside. This one is related to that because f inverse is the inner. It's been a long time since we looked at composite functions. Any questions on what was going on there? A little bit of a detour. We were going to focus more so on the exponentials, logarithms, and a bit of circular functions, but I guess we sort of made our way here. Cool, let's get back on track. So let's just practice a little bit of our log law related stuff. Question 5, just simplifying the logarithms. What I'll do is I'll pull up some of the log law stuff for you guys to reference should you need to. I still have it actually. Shouldn't really need more than these. I'll get them all as a screen grab. And yeah, we'll just give question 5 a shot together, see what we can do. The goal is get it into a single logarithm rather than a sequence. 2 log 10 5 plus 3 log 10 2 minus log 10 20. Usually a bit of guidance around here is to try and make sure there's no coefficients involved, trying to do some sort of arrangement to remove the coefficients from our expression. How might we go ahead and do that? Yep, a 1 out of 3 chance of picking the right law, basically. One of which is working with the coefficients of a logarithm. I'll even have it on the screen share as well. So it's either product law, quotient law, or power law. One of those is going to start working with those coefficients.
We can multiply, we can start off with the power law and then use the product law, and then you can use the product and the quotient law together, right?
Yeah, that's right. So basically, you're right. So we start with our power law stuff to get all those coefficients in there. Basically, the coefficient of 2 is going to come in as a power of the 5. So we're going to have log 10 5 to the power of 2. Similar thing is going to come over here, log 10 2 to the power of 3. And well, this one has no coefficient, unless for whatever reason you wanted to put a -1 in as a coefficient, but that's sort of a bit not advised necessarily. And yeah, that's power law. Basically, if you have a coefficient, that can come in as a power of the entire bracket. Then you were mentioning the product and quotient law. Those simply state that whenever you have an addition or subtraction between two logarithms, you can combine them using multiplication or division into a single logarithm. So basically, because we have plus here, we're now going to have log 10 5 squared times 2 to the power of 3. And because we had a minus there, that's going to be a division of that 20 term. That gets it all into one single logarithm. All we're going to do now is simplify the arithmetic. Log 10, so 5 squared is 25, 248 over 20. Maybe I should have actually done a little bit differently. Maybe instead of expanding it out, probably a better approach would be to break it down into factors. So 5 squared, 2 cubed, and then splitting the 20. So 20 could be 10 by 2, it could be 5 by 4, which is probably a bit better. 5 by 4, which is 2 squared. By doing that, you can now cancel out factors a little bit nicer. For instance, there's a 5 here and a copy of a 5 up there. There's 2's here, and, well, yeah, it's going to neatly basically bring it down into 5 by 2, which is 10. Log 10, 10, and that has a simplification involved. I'll pull up all of the logarithm identities, see if you can spot which one is applicable. Those are available on the screen share right now. One of these is available for us. Got a 1 in 5 chance if you just want to shoot one out. Otherwise, think about
What's the question again?
Simplifying log 10, 10. So one of these identities that I have on the screen share is relevant. Did you actually say it? I think I might have heard you.
The one?
It's 1. Yeah, correct. So that's the log A equals 1 identity. A being the base and A being the bracket. Or in other words, if the base and bracket of the logarithm are the same, that will always equal 1. So final answer for that entire question is going to be 1. Cool. Okay, that should be about it for that. Everything else is just a bit more of that going on. Question 2 looks like, 12, sorry, looks like it's going to be the next step up of exponentials related stuff. Let's give that a shot. Okay, so that's going to be 2 to the power of 4x minus 5 by 2 to the power of 2x plus 4 equals 0. So there's a few main ways we go about solving exponential equations when an exponential equals a certain number. I'll briefly talk about the main ones, and we'll see if you can identify which of those are going to be applicable here. So let's have a look at the screen share. So you've got the equating exponents approach, you've got the quadratic solutions approach, and you've got the logarithms approach. For equating exponents, the idea is you have a bit of a simpler type of equation. You have exponential on one side, you have a number on the other. What you do is you try to get them both into having the same base. Once they have the same base, you can now just look at the exponents, the powers on both of those, and just equate them together. That's one possibility. The other possibility is when you have a more complicated scenario where you've got like multiple exponentials involved, some coefficients, some constants. There's just a bit more going on there. The idea here is to look at the most basic version of the exponential that is a common factor of both of them. So for instance, 3 to the power of x is a factor of 3 to the power of 2x, right? They are factored. They could be written as factors of each other, basically. What you do here is you take whatever that factor is and ideally substitute just to make life a little bit easier. And what you'll find by doing that substitution is you end up with a quadratic. From there, you solve the quadratic, plug back in what your substitution is, and then solve those related exponentials with the method we discussed earlier. The last is the logarithmic approach, which we did already. That was when we were working with our inverses, where you get the exponential on its own and flip to logarithm form. We've got 3 options there. Which one seems most applicable to what we have here? Worst case scenario, 1 out of 3 chance of a guess.
It looks like a quadratic.
Sure does, yeah. Quadratic solution. It's basically when you have like a complicated looking exponential set of equations, it's probably going to be option 2, the quadratic set of solutions. So, based on that, let's see if we can follow the procedure. First things first, make sure, I've written that to say they should share the same base. Basically, you want to get all these exponentials to be rewritten as common factors of each other. So we've got a 2 to the power of 4x and a 2 to the power of 2x. What's the largest common factor there? Largest common factor, 2 to the power of 4x and 2 to the power of 2x.
Do we look at the coefficients?
Here's yours. This is yours.
Yeah, so probably the coefficients on the exponents, right, like the 4 and the 2, for instance. Yeah, you're basically looking for, that can be one way of thinking about it. They already have the same base, so you can just start looking at coefficient common factors. Because we're looking to try and do a big substitution that'll make this thing look like a quadratic.
Yeah, we can sort 2x with any other variable.
That's it. 2 to the power of 2x is going to be some variable, because 2 to the power of 2x is a factor of 2 to the power of 4x, right? It's just double that. as far as exponents are concerned. So basically, we're going to end up with a squared, because our index laws say that's how that one works. And then minus 5a plus 4 equals 0. Right, the a is directly replacing this. Because this is 2 times bigger, it's going to have a 2 that's left over there. This is just a quadratic. We can solve it many different ways. There's probably a common factorizing approach here. Let's see, -4, -1. A minus 4, a minus 1. That's just the add together times together method. Two things multiplying to give 4 that also add together to give -5. -4 times -1 gets you the 4. -4 plus -1 gets you the -5. That's going to, via null factor law, get us a equals 4 and a equals 1, the opposite of those terms. And finally, because a is the same as 2 to the power of 2x, we can now put that back in. 2 to the power of 2x equals 4. 2 to the power of 2x equals 1. At this stage, we now move on to the first way to solve exponentials, which is to basically get both sides of the equation into the same base, and then from there equate the exponents. I've got an example of that up on the screen share. How can we apply that to our set of equations now?
We can set the we can use logs and set the bases.
Yeah, that's totally accurate. Actually, we could do logs as well. That's also perfectly fine. So yeah, if we were to do logs here, you'd have log 2 on both sides because the base of the exponential is 2. So you're going to have essentially 2x equals log 2 of 4. And for this one here, it would be, again, 2x, but this one will equal log 2 of 1. In both cases, you want to get the x on its own, finally. So you're going to have x equals half log 2, 4, and x equals half log 2, 1. The challenge with logs is these are not fully simplified just yet. We need to start using our log laws once again to start, or even the identities, actually, rather, to try and simplify things even further. So let's even, probably this right-hand side one's going to be the easiest to simplify for now. Let's have a think about that one. What could that simplify all the way down to?
Log based any number to 1 is always 0.
That's right. So final answer, x equals 0 for that one there, because log 2, 1 is now going to go to 0. Yeah. This one, bit trickier. How's this going to start simplifying?
Log base 2 of 4 is 2.
Yep, it is. How do you know? So what's the logic behind that?
2 squared is 4.
Yeah, that's right. So fundamentals of logs, the way this works is you basically say, what number do I raise this thing to the power of to make it equal that? In which case you get the answer 2. So finally you get x equals half times 2, which of course is just going to give you 1. The other way you could have potentially done it, if you forget that for whatever reason, or forget the order in which you're supposed to do that, you can use your log law, bring this in as a power of a half, square rooting that down to 2, and then finally log 2 of 2 is 1. That's the logarithms approach there. The alternative would have been to equate exponents. So basically writing both of these into the same base of 2. So what that would look like in that case would be 2 to the power of 2x equals 2 squared, right? Because 2 squared is 4. And then the other one, 2 to the power of 2x equals 2 to the power of 0, because anything to the power of 0 is 1. Then from there, because they have the same base, you only have to look at the exponents, which quickly shows you, okay, 2x equals 2, x equals 1, 2x equals 0, x equals 0. So while logarithms is perfectly valid and gets you there, for these kinds of questions, it is a little bit faster to do it via the equating exponents route. But again, if you got one method that works, that's better than a lot of people who have no methods that work. So if you got one, that's fine. Cool. Okay, that's that. Next up, question 13 gets us back to our circular functions related stuff. Let's take a look at that. So this is a solve type of equation. We've got sine of 3x over 2 is equal to 1/2, and we're solving that from negative pi to pi, inclusive. My OneNote likes to bleed a little bit, doesn't it? I'll draw something and then it'll just sort of glitch out on the screen. Anyway, cool. So this is a solving circular functions type of question. I'll pull up some notes for that if you guys want to follow a procedure, or otherwise let me know how might we start this.
You can find sine of x equals to 1/2. Find what x is.
Yep.
Well, you can find the first quadrant value.
Yeah, that's right. So basically starting out by saying sine equals 1/2. Where on the unit circle do we have sine equals 1/2? Yeah, absolutely. I've got a copy of the unit circle up on the screen share. Where does sine equal 1/2 on the unit circle?
30 degrees.
30 degrees is one of them? Yep.
So it's pi over 6.
Yeah, so pi over 6, sure, same thing. So that'll be one of our solutions, pi over 6. There's another spot on the unit circle as well, which we may not use the exact value of it, but it'll come in handy just to know where it is. Where's the other spot?
In the second quadrant, that's a 5 pi over 6.
That's it. Yeah. So basically what he's doing there is he's saying, okay, sine is the y value, so every y coordinate that equals 1/2, I want to know what the angle is that's associated with it. Because the domain was given in terms of pi, radians, we want to also give our angles with radians as well. So we've located our two spots. The way it works is, whatever's on the inside of your circular function, which in this case is 3x over 2, that is now going to be equal to those two values. Because remember, the thing on the inside of a circular function is the angle. So the angles that we just found are what we're going to make those equal to. That's the initial run through of doing this. From there, we want to start looking at our domain. So we're only allowed to have values when all is said and done between negative pi and pi. Now I do specify when all is said and done because we still got to rearrange this thing finally for x. So for instance, that would mean multiplying everything by 2 and dividing everything by 3. 3x equals pi on 3, comma 5 pi on 3, and then finally dividing it down, pi on 9, 5 pi on 9, both of which do now, well, they already did fit within our domain a little bit, but now we can definitely verify they do even further. So it's this end result that has to now fit between negative pi and pi. We've done a positive cycle. How would we do a negative cycle if it exists?
The negative cycle doesn't exist. Well, there aren't any values in the negative cycle.
Potentially. It's cutting it close, I would say. At least from an initial analysis. I don't know if you've done the whole procedure yet. I'm assuming you're looking at the fact that this is negative pi, and that's as far as you're thinking about it so far?
Oh, wait, yeah.
Yeah.
The domain is changed.
Yeah, because you
So,
got these coefficients that divide it down at the end, means that numbers that otherwise wouldn't fit may end up fitting, which is why
yeah, so there's one more value.
probably going to be one if we were to sort of eyeball it, maybe two. So typically what I'll do is I'll get the first two positive solutions, get the first two negative solutions, divide it all down, and then see, do I feel like I have room for more to fit in there? As for how you get the negative solutions, essentially you're just going backwards around the unit circle. Or alternatively, you're doing the whole flip method. Like for instance, looking at the positive version, flipping up, and then putting a negative sign on that. So for instance, this here would be negative 7 pi over 6, and this here would be negative 11 pi over 6. I don't think negative 11 pi over 6 is going to work for this, but we'll write it down anyway, just in case. So let's get those down. Negative 7 pi over 6, negative 11 pi over 6. This stage was multiplying everything by 2, so it's going to be negative 7 pi over 3 and negative 11 pi over 3. And then finally divide everything down by 3, negative 7 pi over 9, which does now fit.
So first you find...
Yeah, go for it. You might have muted yourself by accident.
that was my bad, just an accident.
Oh, sure. Yeah, so as we sort of expected, this one ended up being a little bit too big, right? Negative 11 pi over 9 is a bit out of the range of this one, but this one does now fit, right? 7 is less than 9. So all of these we don't care about. We know we've gone too big on there, and just to be safe, you might want to do the second cycle of the positive solutions just to see, but this is pretty damn close to 9 pi over 9. So you really only want to do that if you're a little bit unsure. Like for instance, if we just sort of validate that now, the next one, if you keep counting around, should be 13 pi over 6. So 13 pi over 6, multiplying that by 2 gets you 13 pi over 3, and then that's going to become 13 pi over 9, which, as we kind of expected, a bit too big. So, final set of solutions, that. This is what most people will do. They'll do it in this way, get the first two positive, get the first two negative, and then take it from there. If you wanted to, you could actually figure out ahead of time exactly what will fit and what won't. It is a bit more work up front, but it'll save you... It's kind of just like, do you prefer to do guess or check, or do you prefer to just like know ahead of time exactly what you need? The way to know exactly ahead of time what you need is based around this here, the 3x over 2. What you can do is use a substitution. So what we can say is something like u equals 3x over 2, and then fix this domain in terms of u now. So basically sub in both of those x values into that equation and get them in terms of that new variable. So negative pi goes in there to give you negative 3 pi on 2. Pi goes in there to give you positive 3 pi on 2. This is where you now compare this domain to this stage up here when you're getting your first set of initial values. That way you'll know before doing all the arithmetic how far you have to go, because you can just count around the unit circle a bunch of times, and then as soon as you exceed this, you know when to stop. That's if you want. It just kind of shifts most of the effort on this stage rather than these stages. This is probably faster because you guess and check. You kind of get a feel for how much wiggle room you have as you do more of these, but doing it this way, you probably have a bit more certainty. It's really a personal preference thing, though. If there's anything to clarify there, let me know. Otherwise, Yeah, otherwise question 14 should be a fairly chill one, just stating range and period of the circular function. Those are just some fundamentals of circular functions. Range and period. We know what range is from our earlier discussion. Period is a new term for today, but certainly not a new term in general. Okay, so range of any function is just all the possible y values that it can have. As a reminder, for circular functions, specifically we had cos. Basic cos kind of looks like this, right? You've got a bit of a wave-like pattern. The peak and the trough of your graph is going to be determined by the factor at the front, right? So this 3, for instance, gives you a peak of 3 and a trough of -3. The other thing that can influence that are any vertical translations. So if you have a plus on the outside, for instance, you take whatever the initial peak and trough are and shift it up by that value. So sine, there's a coefficient of 1 here. It would normally have a peak at 1 and a trough of -1. Shifting those up by 2, this -1 goes up 2 down to here at 1. And the peak that we would have had goes up by 2 to 3. So if we look at what we have here, we have a dilation factor, the amplitude, of 3 there, and we have a shift up by 5. This 3 means that we initially have a range of plus minus 3, so -3 to, try that again, -3 to +3. And then the translation, the +5 that's at the front there, that's going to shift both of those values up by 5. So that's going to give us 2 and 5, 6, 7, 8. Final answer, the range would therefore be from 2 to 8 for this one. As for the period, that's a specific calculation. Anyone remember how to calculate the period of a circular function?
2 pi over n.
That's it, yeah. So specifically for sine and cos, the period is calculated by 2 pi over n, like that on the screen share. By definition, the period is how long it takes the circular function to repeat once. So if we look at one of our graphs, that's one cycle. That's how long it takes before it will repeat once. The distance from here to here is considered the period of that. For our one, we're now going to have capital T equals 2 pi divided by n, where n is the coefficient on the x. So that means everything that's multiplying or dividing on the x, of which we have pi over 3. So this would be 2 pi divided by pi over 3, which is better written probably with an actual division symbol. 2 pi divided by pi over 3. Now it's a bit clearer to see how you would flip this around. Division of fractions is the same as multiplying the flipped version of that fraction. Things will now cancel down, giving you a period of 6. So capital T, period equals 6. It's a unitless answer because there was no background information given for this circular function specifically. We don't know what h is, we don't know what x is. They're just values on an x and y axis. In a lot of your application questions, there will be some actual background. A very typical one is going to be like the wave depth or wave height, where time will be your x-axis and height or the depth of the wave will be on the y-axis. Under those circumstances, you might use hours, minutes, seconds, whatever it is for period. It's usually a measurement of time more than anything else. Okay, won't go with part B. That's just going to be a duplicate of question 13, more or less. Let's see, what else have we got? Exponentials, logs, circular functions. Not quite. Let's go with 25. It's using exponentials, but we got a bit of a different take on it. Just because it's exponentials doesn't necessarily mean we will need exponential methods for this in particular. Let's see how we go. So we're starting with a completely generic exponential with a base of e, and we're given a few known values that exist on that curve, on that function. Our goal is to figure out the values of a and k. I'll start writing out all the key information. In the meantime, have a think about how you might solve those values. The hint will be that this being an exponential won't really matter. You'll solve it the same way as you solve these kinds of questions with polynomials, with the hyperbola, the truncus, any type of graph or function. Actually, next week on Monday, we're going to do a full lesson on these kinds of questions exactly, specifically around the hyperbola, truncus, and square root. Okay, seems like we might need a bit of practice. So these pairings of values matter. So these are independent of each other and related within their little boxes, right? Like when y equals 4, t is specifically 1. So in other words, if we were to start putting that into the function that we have, if it starts to not be blurry, if we sub in 0.1, it'll now look like 4 equals a e to the k times t, where t is 1. Or in other words, 4 equals a e to the k. Subbing in the other point, we would do very similar. 10 for y and 2 for t. A, e, k, 2, or in other words, 10 equals a, e to the 2, k. What this has achieved is it's got two separate equations with only two unknowns. E doesn't count. E is kind of like pi, where it's a special number. E is approximately 2.71, whatever. Pi, let's try that again. Pi is roughly 3.14. These are special irrational numbers. They don't count as variables. So we got A, we got K, we got A, we got K. Two equations, two unknowns. This should now start looking a bit more like what we're used to with these kinds of questions. When we have this scenario of two equations and two unknowns, what do we usually do?
Elimination.
Yeah, elimination will work pretty good here. So elimination, one of the things I would probably do here would be a division. I noticed that on both sides of these equations, a is a coefficient. So if you do a division, then the a's will cancel out. So basically you do 4 over 10 equals a over a.
I think it would make more sense to do it the other way around.
Yeah, if you want. Sure. Other way. So yeah, what he's highlighting there is you can do whatever order you want there. So 10 over 4 equals a over a, and then you have the 2k on top of the 1k thing. 10 over 4, that's just 5 over 2. A over a cancels out. E to the k will end up being the final thing there. From there, we've done these kinds of questions before. Exponential on one side, value on the other. So this is a logarithm swap. Natural log 5 over 2 equals k. once you have one variable, you plug that into one of the equations, whichever one you prefer, and then just solve for the remaining variable, the easiest of which is going to be this first equation over here. So 4 equals a e to the k, which is now natural log 5 on 2. And yeah, 4 over a, so we can get our exponential on its own, flip everything around. So we're going to have the natural log 5 on 2 equals natural log 4 on a. Because both sides are exactly natural log, we can pretty much ignore that they say natural log and just work off of what's left. So 5 on 2 equals 4 on a. And then, yeah, we're just doing a bit of algebra here. 5a from that, and then 4 2s are 8. A equals 8 on 5. Cool. I've just realized I've hit time on that, so I guess this will be the last one we have a look at. Unless there's any further clarifications, I'll let you enjoy the rest of your day. Thanks, guys. We're in a standoff. One of you's got to shoot first. Yeah, any questions at all? That or you're both AFK.
Mm-hmm. Are we? Can we? Wait. Can we look at a bit of calculus next class?
Calculus next class.
Yeah.
Let's see. So it's going to be a review week thing. Yeah. I'll make a note for calculus for next class. If there's anything specifically within it, let me know. Otherwise, I'll just look at the week.
We just started calculus in 3-4. So yeah, I'm just hoping I can get a little bit more practice in that.
Yeah.
Especially with exponential and logarithms.
Yeah, sick. We can definitely do that, and even class 2. So this class again next week. It's a review week, so I can even make sure we address the derivative stuff again there. That'll basically put us ahead of the schedule I've got going on. So I'll just sort of bring everything forward to make that happen. Easy. You got one, Taihan?
No, all good.
No,
Thanks,
all good.
Chris.
Easy. All right. Well, thanks, guys. If there's anything further, you know how to reach me. Sweet.
Thank you.
Thanks. Have a good day.
You too.